this integral. It's super amazing. In fact, not the real version of it, even though everything is real, but rather we'll talk about the complex version of this, and that's the one that's going to give us very, very nice result. And you guys are going to like it so much. I didn't come with the following though. I want to thank my dear ZVH, right? He was the one who showed me how to get this awesome result. And we begin by looking at the integral from 0 to pi over 2, ln of 2 times cosine x dx. Everything is real, and the first step is to make it complex. So let's talk about the following. This is the same as integrating from 0 to pi over 2, ln, the 2 is still 2, and we'll be using the complex definition of cosine for this, which is e to the ix plus e to the negative ix all over 2. And if you want to see why this is true, you can check out my video. The link is in the description. And you see that the two cancel each other out nicely. That's good. And here we have the integral from 0 to pi over 2 ln. From here to here, I will factor out the e to the ix, e to the positive ix. And we see that from here, we get 1 plus. And once we factor out e to the ix, we will have to minus ix from this exponent. So we get e to the negative 2ix right here. And if you multiply this out, you see we get that back. So we know we did this right. And of course, we are still have that dx. We're still in the x world. And now we see that this is pretty much the product of two things inside of the ln. So we can write this down as the sum of the ln plus the other ln, right? And we can also write them as two separate integrals. Therefore, I will just write this down. This is the integral from 0 to pi over 2. First one is ln of e to the ix, and then we will just close this integral. Secondly, we add integral from 0 to pi over 2 ln of this 1 plus e to the negative 2ix dx. And if I have a choice, if I'm taking a test for something, I will choose to do this one over this one, of course, because ln and e, they cancel each other out. So right here, we're pretty much just integrating ix in the x world. And to do so, remember, I is just like a constant. So you keep it, and then you add 1 to the power. 1 plus 1 is 2, divided by the power, which is over 2 here. And then you have x squared right here, and then you go from 0 to pi over 2. And perhaps we'll finish this first. Why not? Plug in pi over 2 here, you get I over 2, and then you have pi over 2 square, and then minus I over 2, and then plugging 0 square. This is pi squared over 4. 4 times 2 on the bottom is just over 8. So therefore, we get I pi squared on the top over 8, like this. And this is, of course, 0, so we don't need to worry about that. And now the harder part is this right here. I don't want to try integration by parts. I don't want to try substitution. I will just use series for this. So check this out. Which series? Of course, ln of 1 plus something, right? So here we go. Let me make a note right here for you guys. Well, we know that ln of 1 plus z, and the reason I'm using z is because here we have a complex number. This right here is equal to the following: z minus z squared over 2, no factorial by the way, and then plus z to the third power over 3, and then minus z to the fourth power over 4, and then plus, so on, so on, so on. And if you want to see why this is true, once again, you can check out my video. The link will be in the description. And perhaps let's talk about slightly technical part, the radius of convergence. This right here, it's only legit if absolute value of z, and remember z is a complex number, so if you take the absolute value, meaning that you're trying to find the distance of that complex number from the origin. If that distance is, and with the exception that z cannot be -1, then this right here converges. Okay? And once again, detailed explanation, the link will be in the description. Okay, here we have this part, e to the negative 2ix. We can simply first plug in this into all the z and then integrate. That would be the strategy. So here we go. Let's take a look of what's ln of 1 plus e to the negative 2ix, like this. Okay, I will just first plug in this into all the z's, and the thing I will do is that I will not multiply out the exponents. I'll just leave it as how they are. You'll see why. Anyway, first of all, I will do this into here, so which is e to the negative 2ix. And then next, I will just put down minus, plugging this in here. We know that we will have to multiply the exponent with that, right? Because you have this square. I will keep this 2 in blue and then the rest in red. So we will have e to the negative, let me put down the 2 first, original power right here, and then times 2ix like that, and then over 2 like this, okay? And then next, we do the same thing, plugging this in here. I will keep the 3 in blue, so we pretty much will have e to the negative 3 times 2ix over 3. And then the last one on the list that we have, of course this one goes on forever, but the one that we will do is we minus e to the negative 4 times 2ix over 4 and so on, okay? All right, this right here is just the function inside. Now let's talk about integration. And first of all, let's just integrate with respect to x, okay? So let's put this down. And the good thing is that we have e to the constant times x. And this is x to the first power. So we can just do the following. The integral of this is that you keep this part, but you divide it by the derivative of the input function. It's pretty much the coefficient. So the first one is going to give us e to the negative 2ix over negative 2i like this, okay? And then next, I'm going to minus. Here we will have, once again, this part pretty much stays the same. I will write it as e to the negative 2 times 2ix. And I have this 2 originally, but I will have to divide it by the coefficient. Namely, I will have to divide it by negative 2 times 2i like this. And once again, I am not multiplying out anything, okay? And the next one is plus, and on the top we'll just write it as e to the negative 3 times 2ix over this 3, and then we divide it by the coefficient, namely negative 3 times 2 times I. Okay, so far so good, huh? And then minus, this is like doing accounting, man. It's like you keep track of everything and things like that. And yeah, in fact, this is like my 4th or 5th time recording this problem because I messed up my organization of my work. Anyway, minus 4 times 2 times I, or negative 4 times 2 times I, all that stuff. Okay, that's how we integrate that guy. Nice, huh? And then we will plug in numbers, of course. 0 to pi over 2, 0 to pi over 2. However, before we plug in the numbers, I'm going to do some factoring. This is why that I did not multiply out anything on the bottom, however. Because we notice everybody has negative 2i on the denominator, right? You see, negative 2i here, and negative 2i, negative 2i. Let me just do it. This is the negative, and then the 2i, and then negative 2i. And also, you see, this is 3, and then multiply with this 3. Something is going to be very pretty, okay? So I will factor things out and do some algebra before I plug in the pi over 2 and things like that. Let me just factor out 1 over negative 2i all the way to the front, okay? And then we will have, the first term is just e to the negative 2ix like this. And you know what, let me just change this to red to make me happy a little bit. Negative 2i, because everything is in red, yeah, including this one. Anyway, this is that, and the next is minus. I will still write it as e to the negative 2 times I, 2 times 2 times ix, okay, 2 times ix. I haven't multiplied out anything yet, you know why. On the denominator though, we see that we have 2 times 2. I will write it as 2 squared, okay? And then next, I will add, on the top is still e to the negative 3 times 2ix. And then on the bottom, we have 3 times 3. So that's 3 squared. And once again, I factor out all the negatives right here already. So these signs, they stay the same. And then minus e to the negative 4 times 2ix over 4 times 4, which is 4 squared. And dot dot dot, like that. And now we are talking about going from 0 to pi over 2. And I am not going to show you guys plugging this because that would be a lot to write. So here is the deal, okay? Notice everybody here is pretty much having the negative 2ix, right? 2ix, 2ix, 2ix. And when we plug in pi over 2 here, the 2 in blue and this 2 in black, they will cancel things out. And you'll pretty much be talking about with a 1 left, 2, 3, 4 left, and also the negative, things like that. So here is a note I will make for you guys. This right here is just another note, okay? We pretty much will have the following. E to the negative ni pi, okay? Everybody is going to have the I and also the pi, okay? And everybody has the negative in the exponent. Now it's just a matter of what this n is. And in fact, we only have 2 choices. This right here will be either negative 1 or positive 1. This right here will be negative 1 if n is odd. And on the other hand, this right here will give us positive 1 if n is even. And now I'm just going to be plugging pi over 2 into all the x's right here. And this is going to be really helpful. First of all, let me just write down the 1 over negative 2i all the way in the front. So open a big parentheses, okay? And let's see. I will first plug in pi over 2 into this x. And we see that this 2 and that 2 will cancel. So we have a 1 right here left. So this is technically negative 1i pi. And that's going to be this situation. So we end up with negative 1, okay? And then I will maintain this minus. And then I will plug in pi over 2 into this x. This 2 and that 2 cancel, so we have this 2 right here. I'm just looking at this number, which is 2, which is the even situation, which is going to be a 1 on the top. So we have 1 over 2 squared, and then we continue. Next, we maintain the plus first. Plugging pi over 2 into this x, the 2's will cancel. This is a 3, so that's an odd situation that will give us negative 1 on the top over 3 squared. And then next, when we plug in this, you see the 2 will cancel, but this is a 4. So that means we will have a 1 on the top. Maintain the minus though, and then you have the 1 over 4 squared, and so on, so on, so on. And you see that in this parentheses here, this is the result that we will get when we plug in pi over 2 into all the x's. And now I will subtract. Perhaps I'll make this red so that it's slightly more clear. Okay, subtract. Next, I will plug in 0 into all the x's. And this is very nice because e to the 0's power is just 1. So first we get positive 1. Next we get the minus stays, and then we still get a 1 and over 2 squared. And then we maintain the plus, and this is 1 over 3 squared, and then minus 1 over 4 squared, and then plus dot dot dot, so on. Close that, and then close that, okay? So it depends on how you want to draw the parentheses. Perhaps this is slightly prettier. Okay, now pretty things happen again. Okay, if you look at the first term, this is negative 1 minus 1. Okay, leave that. But you see negative 1 over 2 squared minus minus becomes plus. In another word, this and that will cancel each other out. This and that cancel each other out. Next, this term stays. You are going to combine like terms in a second. And then this and that will once again cancel each other out, and so on, so on, so on. And if you see that, we are going to get, we still have this 1 over negative 2i all the way in the front. And then when we do negative 1 minus 1, of course that's negative 2. And then negative 1 over 3 squared minus 1 over 3 squared, that's going to be negative 2 over 3 squared. And if you would like, I could have put down this as negative 2 over 1 squared, right? Because you could write it as 1 squared here to keep the same form. And if you look at the denominator, if you write down more terms, you will really see that the next term is going to be negative 2 over 5 squared, and then negative 2 over 7 squared, and so on, so on, so on. So I will just leave it like this, okay? And of course, the 2 will cancel out here, 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 right? And then the negative distributed in there, you get positive. So that's all good. So let me just keep it as 1 over negative I, like this. Well, actually, that will just write it as 1 over I. The negative will be distributed, so I get positive 1 over 1 squared, positive 1 over 3 squared, positive 1 over 5 squared, and positive next terms and all that. Okay, this is all good, but I don't like to be on the bottom. I like to be on the top. Therefore, I multiply the top and bottom by I real quick. So this right here is once again I squared, which is negative 1. So this right here is technically negative I, okay? Negative I. And then you have all that stuff. 1 over 1 squared plus 1 over 3 squared plus 1 over 5 squared, and so on, so on, so on, okay? And look at this. This right here is this integral. And perhaps some of you guys notice what we are trying to do. And, you know, we're almost there. Oh my God. I'm going to write this down over there. And, of course, you see this integral was just that. I pi squared over 8. So let me just erase this so we will have more space. I will first write down this right here. I pi squared over 8, okay? And I can say bye-bye to this. Next, this whole thing, which by all that is just this. So I will write down minus I, and then we have the parentheses, which with 1 over 1 squared plus 1 over, unfortunately we don't have 2 squares, okay? So it's 3 squares. 3 squared, and we don't have the even squares, okay? So just the 1, 3, 5, the squares of them and all that stuff. Okay, so this is what we have. And now, of course, you notice both terms have the I, so of course we can factor that out. And when you factor out the I, we get pi squared over 8. And we minus this result, so I'll put on parentheses, 1 over 1 squared plus 1 over 3 squared plus 1 over 5 squared plus dot, 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 and so on. Okay, so it seems like if you change this to the complex version of it, we get this result. But remember, originally, this is what's supposed to be a real integral, right? The real deal. At the moment, we see that this is I times a real number. Keep in mind, everything here is real number. So I times a real number, so we can say that this right here is purely imaginary, right? This right here has to be imaginary, whatever I. This has to be just real. So here is the note. Notice, if you take the imaginary part of this real integral, so I'll just put down IM of that integral. When you take the imaginary part of a real integral, this right here has to be 0. That means this imaginary part, which is equal to 0, and the only way for us to happen is that this inside has to be 0. So I will just tell you guys that this must be 0. We must have I times 0 in order to be 0, so that the imaginary part is 0, so that we will end up with the real value for that. And in fact, the real value for that integral is also 0. All in all, we see that pi squared minus this is equal to 0, so I can say this is equal to pi squared over 8. So we observe that. Let's just say observe that. Here's the nice result that we have. 1 over 1 squared plus 1 over 3 squared plus 1 over 5 squared plus dot, dot, dot. This is equal to pi squared over 8. So good. But of course, this is not good enough because this is it's good, but it's not famous enough, huh? The famous version is what? 1 over 1 squared plus 1 over 2 squares plus 1 over 3 squared plus 1 over 4 squared and so on. So let's see if we can use this to come with that result. I will put this down in black. And let's see if I can fit everything here. Now consider, I will just say the following. Let S equal to 1 over 1 square plus 1 over 2 square plus 1 over 3 square plus 1 over 4 square plus dot dot dot, okay? So let's consider this sum, and we'll see that S is equal to, I will put down the R terms first. So I get 1 over 1 square plus 1 over 3 square plus dot dot dot. This is the R terms, okay? And then plus the even terms is 1 over 2 square plus 1 over 4 square plus dot dot dot, okay? Well, this is S, and that's equal to, this right here now we know is pi squared over 8. And we see that this right here, you can look at this as 2 times 1 in the parentheses square, and you can factor out the 2 square. Similarly, this is like saying 2 square times 2 square. The next one is like 2 square times 3 square, and so on. So I can factor out 1 over 2 square like this, okay? And you will see that this inside here becomes 1 over 1 square plus 1 over 2 square plus 1 over 3 square plus dot dot dot. In another word, we see the equation S is equal to pi squared over 8 plus 1 over 4, and this is S. Let's minus 1 over 4s on both sides. This is going to be 3 over 4s, which is equal to pi squared over 8. And of course, S, you multiply by 4 over 3 on both sides. So let me put this down, 4 over 3 times pi squared over 8. You do the little thing to keep people happy. Finally, we see this is equal to pi squared over 6. Oh my god. In another word, this right here, we just proved it with a very elementary step, I would say, because we didn't really use anything high-tech. We did use things that's complex, but nothing really high-tech. We see that this right here, it's actually pi squared over 6. And perhaps, let me just box this famous result. And I will also box this because without this, I cannot get that. So amazing, isn't it?